Welcome to this fourth video lesson on astrophysics. By the end of this video lesson, you should be able to classify stars according to temperature and color, in other words, do spectral classification. You should be able to identify the general regions of star types on a Hertzsprung-Russell or HR diagram. You should be able to understand the term luminosity and explain it, and then state that luminosity of a star may be estimated from its spectrum. Welcome to this fifth video lesson on astrophysics and cosmology. Now, in this video lesson, we are going to basically look at describing the different types of stars. And we are going to do this in relatively great detail. We are going to use what we've learnt about luminosity in previous video lessons. For instance, understand the term luminosity, state the luminosity of a star may be estimated from its spectrum. We're going to look at using the luminosity radius or area and temperature relationship in order to work out some really cool and interesting information about stars, and you're going to come across something that is exceptionally important, and that is you're going to look at the Hertzsprung-Russell diagram, and we're going to look at that in detail. We're going to look at how we can use this HR diagram or HRD in order to gain a deeper insight into the types of stars and their relative luminosities and their surface temperatures. So this is going to prove to be what I think a very exciting video lesson if you are amped about astronomy and cosmology. We now come to a very important concept and tool for astrophysicists when coming to studying stars, namely the Hertzsprung-Russell diagram. So the luminosity relationship L equals sigma A T to the 4 tells us that the luminosity of a star depends on two things. Firstly, the temperature of a star, capital T, the absolute temperature in Kelvin, and then the surface area of a star, A, in square meters. So this means that a star could be very luminous because it is hot, or it can be very luminous because it is big, or both. Now, when plotting the luminosity versus temperature and luminosity versus mass, this leads to some very interesting and insightful patterns that help astrophysicists to learn more about stars. So let's first look at the mass versus luminosity relation. So if the composition of different stars differs, that could mean that there are many different combinations of temperature, size, and luminosity among stars, and this is exactly what we find. But this would mean that this would lead to them being randomly distributed on a luminosity temperature diagram. However, though, the fusion process of more than 90% of all stars converts hydrogen into helium. And so they are in a similar kind of equilibrium. Now, these stars that convert hydrogen into helium as their main source of energy are called main sequence stars. And in essence, their only essential difference is their mass. Now, higher mass stars will have stronger gravitational forces pulling them together, resulting in higher core temperatures, but then also faster rates of nuclear fusion. So more massive main sequence stars will have larger sizes, higher surface temperatures, and brighter luminosities. So here is a luminosity versus mass graph, and we can see here that on the horizontal scale we have the mass of stars in units of what we would call a solar mass, or the mass of the sun. So This is also represented by the symbol mass with this little solar sign there. And similarly, on the vertical axis, the luminosity is in the unit, in the relative unit of the luminosity of the sun, which can also be represented as a capital L with a subscript with this little dot and circle around it. Now, if you look on this graph, you will see that the sun is to be found with that little yellow data point there. So in the bottom left, we have lighter, when we talk about lighter, we mean mass-wise, lighter stars that burn dimmer. At the top left, we have lighter stars that burn brighter than the sun. In the bottom right, we have heavier stars, heavier than the mass of the sun, but they glow dimmer than the sun. And then here we have stars in the top right hand quadrant of this graph that are heavier than the sun and burn brighter. So one can look at this diagram, this graph, in 4 quadrants. But another way to look at it is that there is definitely a pattern here. We see that as the stars get heavier, they also get brighter, because we don't see heavy dim stars here. It's empty. And if you look here, we don't see stars that are lighter and brighter, or certainly none on this graph. So if we look at the trend, it shows that as we move upwards, we get stars that, as their mass increases, so their luminosity increases. And this is because of the fact that as their mass gets greater, so there's more matter in the star. So the gravitational attraction pulling all that matter toward the center of the star is greater, which means a greater rate of fusion, which means a hotter and brighter star. Now, if we look quantitatively at the mass-luminosity relation, then we get this. We get that when the luminosity of a star is compared to the luminosity of the sun, so that's a relative quantity, then we get that it's dependent on the mass of the star's relationship to the mass of the sun. So the mass over the sun, that's also relative. And it's to some power. Now, the value varies with the mass of the star. This value of A varies depending upon the type of star. But to a good approximation, we find that most of the main sequence stars have an A value approximately around 3.5. Now, because of the fact that luminosity is dependent on absolute temperature to the power 4, we can then say that the luminosity varies approximately in the same way to the 4th power of the mass in units of the sun's mass. So practically, what does that mean? Well, for example, to illustrate, if star A has twice the mass of star B, star will have a luminosity approximately 2 to the power 4. In other words, 16 times greater luminosity than star B. So let's just state that again, that if star A has twice the mass of star B, then star A's luminosity is going to be twice 2 to the power 4, which means it's going to be 16 times more luminous. So this means that the rate of nuclear fusion in star A will be much higher in order to produce that luminosity, with also a correspondingly shorter lifetime than star B. So the bigger, more luminous stars don't last as long. So the factor A will be different for stars, and it's little a. The factor little a will be different for stars that are off the main sequence, which we are going to look at soon enough. So now we come to the temperature-luminosity relation. Now, plotting the luminosity versus temperature results in a graph known as the Hertzsprung-Russell diagram, or an HRD. And this was named after two scientists who independently plotted these variables for stars during the early 20th century. Now, when you look at this and you look at the significance of it, this was a huge amount of work, and a very significant work that they did, considering that in the early 20th century they didn't have the technology that we have today with space-based telescopes and with the very sophisticated electronics that we can use nowadays to process imagery that we can get from ground-based telescopes. So this was a significant scientific discovery. So looking at this, we've got luminosity, and it's compared to the sun, so it's in the units of the sun, but it's really a relative scale. So it's whatever is here. Here we see this is equal to the sun. We see the sun is plotted there, but now it's luminosity versus temperature. So if we look at this, we see there's the sun. The luminosity compared to the sun is obviously 1, because we're comparing the sun's luminosity to itself. If we go down, we see that we're around about 6,000 Kelvin there, probably around about 5,800 Kelvin for the surface of the sun, which we know is the case. Now, along here is what we call the main sequence. These are the main sequence stars, and we can see it moves up and down. But this is strange, because shouldn't it be moving like this? Well, this is where it's different, because if you look at the scale, the surface temperature in degrees, all right, this then looks strange, because we're going from 30,000 down to 10,000 to 6,000 to 3,000. So it's going from high to low. So the scale is actually the opposite way around. Okay. Now, the other thing I would like to mention to you is that when you are working on the scale of these temperatures, whether you work in degrees Celsius or whether you work in Kelvin, doesn't really make that much of a difference, because the difference between them is only 273. So that is why they speak about degrees here. It would be degrees Celsius, but pretty much the same for Kelvin. Now, looking here, you find here you have stars with very, very high temperatures. Here you're going to have stars with very low temperatures. And here you're going to have stars with very low luminosities. And here you're going to have stars with very high luminosities. But now, this is a beautiful diagram rendered in color. There's something I'd like you to note about the color here compared to the electromagnetic spectrum. Well, it's red, orange, yellow, green, blue, indigo, violet. As you can see, we're going through there. We're seeing that. Now, remember that the color and the temperature are linked. And the more energetic, the more it goes toward the blue, because blue photons have a higher energy per photon. And red photons have a lower energy. And we know this because the energy of a photon is equal to Planck's constant times the frequency of the electromagnetic radiation. So this is a direct proportionality, because h is Planck's constant 6,63 times 10 to the negative 34 joule seconds. It's a physical constant. It's the smallest of physical constants in normal physics. And the frequency is what we perceive as color. So what we have here is a very, very powerful tool, because what it's linking is luminosity of stars that we observe in the universe through our telescopes with the surface temperature and their color. So we can see that we get big stars that are blue, and we get small stars that have got bluish color. Find here in the white part we get dwarfs. We get big giant stars here. Right, these are interesting down the bottom here. We'll talk about them later on, but you can see along this line, that's approximately a tenth. Those stars have a tenth of the radius of the sun. Along here, the stars have approximately the radius of the sun. You can see not that many. The sun is a dwarf star. And along here, we have stars that have a radius of at least 10 solar radii, so they are huge. Considering that the sun is approximately 1 million kilometers in diameter, that would make the radius of the sun about 500,000 kilometers, 500,000 kilometers. So if you have a star that's 10 radii of the sun, then that makes that star 10 million kilometers in diameter. So we've got stars even bigger than that, like these giants, which we're going to talk about in great detail, and then these supergiants up there, which run from red all the way through to blue. So the universe has got huge stars in it beyond human comprehension. But this is really a beautiful tool for astrophysicists to classify stars that we observe in the universe. So just very quickly, let's just summarize that the following features of the HR diagram are important to take cognizance of. That the temperature scale is reversed, as we've mentioned, highest closest to the origin, and then coldest, coolest, furthest away from the origin. The scales are logarithmic due to the enormous differences in the luminosity and temperature of stars, which means it's not linear like we would normally use in school. The diagonal lines are lines of constant solar radius, as we've spoken about. Stars on the bottom right are cool and dim. Stars at the top left are hot and bright. Some stars at the top right are cool and bright. Those are your red giants, orange giants. And other stars bottom left are hot and dim, your white dwarfs. Now, if cool stars are generally dim and hot stars are generally bright, then how can we explain the cool bright stars at the top right and the hot dim stars at the bottom left? So now the answer is in the size of the stars. So for a cool star to be bright, it has to be very large in size. So remember, the luminosity relationship was L equals sigma surface area multiplied by T to the power 4. So to have a high luminosity with a low surface temperature, the A factor, the surface area, has to be huge. And that is obviously for a huge star. So that is how a cool star with a low T can still have a high L if the surface area of the star is very big. Now, conversely, for a hot star to be dim, it must be small. So if you've got a very high T, and I can maybe write it here, so we've got L, luminosity, equals the Stefan-Boltzmann constant, multiplied by the surface area of the star, multiplied by the surface temperature of the star to the power 4. So the temperature plays a major role. So if you have a very you have a very hot star, then this value is going to be very big, which means that the area is going to have to be very small. So this is shown by the mass luminosity diagram that we looked at before. Now, adding the solar radii lines on the HR diagram allows us to see the effects of mass and temperature on luminosity in a single diagram. And this is why it is such a powerful and beautiful tool for us to use. But what does this HR diagram really mean? Well, it is in actual fact the visualization of the life cycle of stars. Now, we have all seen periodic tables, and we see it so much that we can actually take it for granted. And yet the periodic table is actually a documentation, as you will see, of the life cycle of stars in the universe. So it's a beautiful, beautiful pattern. It's a beautiful record of what has happened in the universe. Now, here too, you will see that the HR diagram is a visualization of the life cycle of stars, and we are going to plot the life cycle of certain stars and see how they move across the HR diagram. So stars will occupy different regions on the HR diagram over the course of their lifetime. So let's look at the different regions, the various regions into which the HR diagram is divided. So now we consider the main sequence, which we have already spoken about, the main sequence stars. So most stars are confined to a band stretching diagonally from the top left to the bottom right. So we're looking here, we can see it. We can see that most stars are to be found from the top left all the way down to the bottom right. So at the one end of the main sequence, the stars are large. We can see they have very high temperatures. We see they have very high temperatures, but they also have very, very large radii in comparison to the sun. And because of their high temperature, they have high luminosity, and therefore visually they produce a lot of electromagnetic radiation in the blue region because they have such high surface temperatures, 30,000, 20, 30, 40, 50,000 Kelvin. The very largest of these are called blue giants. And the largest of the large of these up here would be what we call blue supergiants. Now, on the other side, we find as we go down here, we get the red dwarfs. Now, they have a low luminosity, we can see in comparison to the sun. They have a low surface temperature. That's why their color is predominantly, remember, stars produce color according to the simplistic black body radiation curve. When I say simplistic, I don't mean it's simple, I mean it's simpler. It's a good first order approximation compared to the actual spectrum produced, the spectral curve produced by a star. But so the main wavelengths will be in the red here. But it's also got a very low mass. You can see it's 1/10 of the sun. So there's a massive variance, and we find our sun right in the middle there. So our sun is a pretty ordinary star. I mean, we think the sun is like absolutely awesome and it's enormous compared to us. But if you look here, the sun is a very average star, roughly somewhere in the middle of the main sequence, not particularly big compared to these, not particularly small, not particularly hot, and that's something to actually process if you think of how much energy the sun actually produces, to think that it's a yellow dwarf star. So our sun is an average star, average main sequence star in the universe. So any star lying on a given line has the same radius. So if we look along these lines here, all these stars will have the same radius. Okay, so we can see in the sun's radius, if we open it up there a little bit, we'll see that here, all these stars, there's our sun, all these stars that we find will have the same, will be the same physical size as the sun. But you can see you can get hotter stars and you can get cooler stars that are of the same physical size as the sun. So we also see that along these lines that the radius luminosity temperature relationship therefore implies that the luminosity is directly proportional to T4. So T to the power 4. So let's just expand on this. So we know that the luminosity is equal to the Stefan-Boltzmann constant. The surface area of a star, assuming that the stars are basically spherical, is 4 pi r squared for a sphere. That's the surface area. So if the radii of the stars along that particular section are all the same, so let's say we were looking along here. Let's say we were looking along here. Let me use another color. Along there, then all those stars' luminosities would be directly proportional to their surface temperature to the power 4. So now we look at red dwarfs and red giants. So if we look at the HRD, we see that red dwarfs lie on the bottom right of the main sequence. They're cool and have a low luminosity. And these ones are difficult to observe from the Earth because they're obviously not very bright in the night sky. So since the 1970s, though, astronomers realized that red dwarfs are actually of the most common type of star in the sky. The upper right-hand corner of the HR diagram, here we find what they call the red giant region. Yeah. So many of the brightest stars we see in the night sky are red giants, and they form a third distinct class of stars on the HR diagram, very different in their properties from both main sequence stars and white dwarfs. So this is the red giant region of the HRD, Hertzsprung-Russell diagram. For instance, Aldebaran and Betelgeuse are two of the most prominent red giants that we can see from Earth. To give you an idea of the scale of these behemoths, these monster stars, if Betelgeuse were placed at the same position as the Sun, now you can fit 1.3 million Earths into the Sun, approximately. Now, if you put Betelgeuse where the Sun is, it would engulf all the planets up to Jupiter. So we've got Earth, then we've got Mars, then we've got Jupiter. So can you imagine the scale of a single star if it's that size? A true giant. Now let's look at blue giants and white dwarfs. So if we now look in the top left here, the bright blue O-type stars, remember the O-type stars are the hottest stars, in the upper left of the main sequence in particular here are about 10 times larger than the Sun. And therefore because they are hot, they have a very high surface temperature. Because they're O stars, they are blue. And because of their radii, they are referred to as giants. So these are blue giants. The very largest are called blue supergiants, which we would find up here, right up at the top here. These are the giants, and then going up above this line, you get the supergiants. Now, the O and B type supergiants are extremely rare, with only one star in 10,000 falling into these categories. So as we know, most stars lie in the main sequence. Okay, now below the main sequence is called a region of white dwarfs, and they glow white hot, which is very hot. That's in the region of 10,000 plus Kelvin. But you can see within this white dwarf region, you've got also, the universe is a very big place. That's the greatest understatement I could make, is that you've got all sorts of varieties. But you see, there would be a white dwarf, be sitting at about maybe 8,000 or 9,000 Kelvin, right, but much smaller than a tenth of the sun. You see, there's a tenth of the radius of the sun. Now, so in astronomy, the term dwarf refers to any star of radius comparable to or smaller than the sun, because the sun itself is also a dwarf, a yellow dwarf. Now, something else important to note, that there's no single HR diagram, but many such diagrams, and they can be constructed depending upon which stars are observed. So this is just a generalized diagram to show the main features. But there are also other features such as the instability strip, and obviously, like the periodic table, the deeper you go into astrophysics and cosmology, the more you can see out of a tool like this. Now, once again, keep in mind that stars will change their position on the HR diagram over millions of years as they burn their hydrogen. Because remember, here, these stars basically are using, they're burning hydrogen into helium. But now, as your stars get heavier, they start to burn using the CNO cycle, burning heavier elements. That's now if the stars are very, very big, as we've discussed before. But even so, even a star like ours, when it's old enough, will actually move position from where it is on the HR diagram, depending upon mass. But that's something we're going to discuss in greater detail later on in this extremely interesting topic. So let's now do some mathematics. Let's look at a mathematical problem. So it says, estimate the luminosity and the surface area of a main sequence star of type A. The sun has a luminosity of 3,83 times 10 to the 26 watts. Remember, watts is the unit for power, unit for luminosity, which is joules per second. So what we do firstly is we go to the table. Now, obviously, we would not expect you to know this table to every detail off by heart. Okay, so we have this table, and it's a type A star has a surface temperature of 7,500 Kelvin to 10,000 Kelvin. So we've got a type A star there, so that would be a white star, as we would call it, a white star. So that would sit sort of in the middle of the HR diagram, between left and right. So now we can calculate the average of the lower limit and the upper limit. So 7,500 Kelvin plus 10,000 Kelvin divided by 2 gives us 8,750 Kelvin. We now look at the HRD, and we use this now as a tool to help us. So we go to approximately 8,750 Kelvin on the temperature scale, and then we draw a line up through the white dwarfs to the middle of the thickness, the band of the main sequence, because we were told it's a main sequence star. So obviously starting there all the way up to there, would be stars that are main sequence stars that would have that temperature. So we are going to go into the middle of that band. That's a safe bet. And then taking that point and then projecting it leftwards to the luminosity axis, we find that it sits approximately between 10 and 100 times the luminosity of the sun. So we're going to go with approximately 50. It definitely is an approximation, and so there's definitely uncertainty and error in it, but let's go with a nice round number. Let's go with about 50, just for the sake of this example. Now you will see that we also use this symbol, and that is actually also a symbol for solar. So this is the a solar luminosity. So that's the luminosity of the sun. Okay. Now we were given that the luminosity of the sun is 3,83 times 10 to the 26 watts. So multiply this by 50, and we get that the luminosity of this particular star is approximately, and it's important to state that it's approximate, because as you can see, we definitely have made some fairly big approximations, assumptions. So it's always good as a scientist, as a physicist, to always be explicit about the uncertainty as much as you possibly can. So we put that approximation approximately equal to 1,915 times 10 to the 28 watts. Now, using the luminosity relationship, that the luminosity equals the Stefan-Boltzmann constant multiplied by the surface area of the star multiplied by the absolute temperature to the power 4. We substitute the relevant values in. The Stefan-Boltzmann constant is something that will be given to you in your tests and exams, 5,67 times 10 to the negative 8, multiplied by the unknown surface area, multiplied by the average surface temperature, 8,750 Kelvin to the power 4. We now take these two values, the product of these two values, and we divide it into the luminosity value, as we can see here. And we get that the approximate area is equal to 5,816 times 10 to the 19 square meters, which means it is a huge number. So in this video lesson, we have looked at the luminosity mass relationship and the graph that we get from that, which produces a roughly linear relationship based on observations, an increasing relationship when one works from increasing from small mass to big mass stars, we get an increase in the luminosity on average. Then we looked at the luminosity temperature relationship, and we looked at the luminosity temperature diagrams, the graphs, the plot, and that gives us the Hertzsprung-Russell diagram, which, as we've seen, is an exceptionally valuable tool. And it really, like the periodic table, it guides us, like the periodic table guides us through the elements, this guides us through the stars that are observed in the universe. We haven't covered all the stars, all the types, like for instance brown dwarfs we haven't looked at yet. We saw there that the temperature scale is switched around, and that on the vertical and on the horizontal axis, the luminosity and the temperature are relative scales to that of the sun. So the sun is our point of reference, obviously. And now we've done a calculation using L equals sigma A T4 and using the OBA classification and the the average temperatures associated with those types of stars, and we are able to extract some pretty neat information from this. So this is the kind of problems you would get in your tests and your exams, and you will be provided with further practice on these types of problems. And I hope that you've been enthralled, you've enjoyed this journey through the groupings of stars and the way that we actually classify stars, considering how huge our universe is, that we sitting on this tiny little planet have actually been able to work this out, and we're able to look into the universe and with deeper insight, and actually are able to look at stars and go, well, okay, if you're that color, then you're approximately that temperature, and you're approximately going to live that long. And we can even, as we go deeper into astrophysics, we can also say, well, if you that luminosity, you are that distance, we can look at, for instance, Doppler shifts, and we look at, for instance, how the universe is expanding, the expansion rate. So we are now able to look out at the universe not only with awe and wonder, but also with insight. And so what a wonderful privilege, what a wonderful window we have in this syllabus to be able to peer deeper into the universe with deeper understanding.